Your types of solids, so if you were getting to the point where you were thinking of only solid substances, you have ionic solids, metallic, molecular solids would be substances that can be made to turn into a solid or exist as a solid in their natural molecular state. They can be London dispersion forces, dipole-dipole, or hydrogen bonding, a wide variety. So ice would be hydrogen bonding, while all three of these are simply London dispersion forces. Atomic solids are always London dispersion. They're always nonpolar. If you look down some of your groups, especially your halogens, where you have you have diatomic elements, you can definitely see by London dispersion forces that you move from a gas to a liquid to a solid. And then, of course, on the high end, you have your network covalent solids. I'll give some notes on those. And those are your stronger bonding diamond, quartz, and silicon. So metallic bonding we've gone over before. Just briefly remind you, metals are crystalline. They have a crystal lattice. They have cations surrounded by an electron sea. These are non-directional bonds, meaning electrons are free to move within the substance. Metals have a wide range of hardness and melting points, but the metallic bonding, their malleability and conductivity are based on that electron sea model. So metal cations floating in a sea of electrons. That's why they're able to conduct electricity, and they are malleable. Your molecular solids, again, as we stated before, are going to be molecules that are turned into solid state by either having large London dispersion forces or dipole-dipole, or cooling them down until their normal liquid state turns into a solid. So I don't want you to think that ice has different bonding than gaseous water. It doesn't. It's hydrogen bonding. You just have more of those hydrogen bonds taking place as you slow down the molecule's motion. Atomic solids, we mentioned before, are elements that are solids at room temperature: iodine, sulfur, so on. So your type of bonding: ionic, metallic, network covalent, dipole-dipole, hydrogen bonding, LDF, and then your types of solids can reflect that: your ionic bonding, your metallic bonding, network covalent bonding, and then molecular and atomic. But your types of intermolecular forces are pretty much ionic, metallic, network covalent, dipole-dipole, hydrogen bonding, and LDF. So your network covalent solid, this is exactly what it sounds like. It's a huge network of covalent bonds, so that the intramolecular forces are the intermolecular forces. It's a giant covalent molecule. Sometimes we call it a network solid or a macromolecule. So these are directional covalent bonds that are holding these structures together. They have hard, high melting points, and they are usually insulators. So you're looking at things like diamond and quartz and silicon. So you know that your carbon is a special atomic solid, since it can have several allotropes, meaning structural forms. Coal is fairly soft and amorphous. Diamond, of course, is the hardest substance on Earth, and it's quite a good insulator of heat and electricity. And then graphite has a very different structure. So you very well may be asked to compare diamond and graphite. So we'll look at their structures in just a bit. Your diamond has an sp3 hybridized carbon. So your sp3 hybridized is connected to 4 other atoms, so it's a bunch of tetrahedrals. sp3 means you have no lone electrons in a multiple bond, you have no delocalized electrons, you have all these strong covalent bonds, and they just bond one carbon to one carbon to one carbon to one carbon. These are very strong sigma bonds, so macromolecule is a really good description, although most people will use network covalent solid. So these are your inter, and they become your intramolecular forces as well. So these strong directional covalent bonds, meaning electrons are bonded between the 2 atoms, means electrons are not free to move. It makes it impossible for electrons to move because they're not delocalized, they're held strongly. So if you're ever asked to explain an insulator, any insulator means electrons are not delocalized, they are directional, they are not free to move. Graphite, on the other hand, is carbons that are sp2 hybridized. And if you remember, with sp2 hybridization, you have a multiple bond, and that unhybridized p orbital exists above and below the plane of those carbon atoms, and that's where electrons are free to move between those planes, just like you see here. So that is why graphite, with its 120-degree bond angles and sp2 hybridization, has pi bonds that extend above and below and carry those electrons. Those electrons are delocalized in the graphite. So comparing the carbons in graphite and diamond would be a good structural question on the exam. Pi bonding networks where electrons are free to move. This also allows the layers to slide by each other. Quartz, silicon dioxide, has a structure very similar to diamond. You can see this huge structure, hard crystalline structure with all of these covalent bonds that are quite strong. So quartz is also a network covalent solid. At the very top end then of your bonding are your quartz and diamond, then your ionic, then your hydrogen bonding, dipole-dipole, and LDF. But remember, within these, there can be quite a bit of overlap. When you're looking at states of matter, you have to assume when you're in the solid state that you have the strongest intermolecular forces for anything. The liquid state has weaker and the gas even weaker. So if something is a solid at room temperature and something else is a liquid at room temperature, the solid absolutely has the strongest intermolecular forces. It also has the lowest vapor pressure because the gas state is not readily occurring on the surface of that solid. With a liquid, you do get some molecules leaving the surface, and of course the gas state. In the gas state, all molecules are in the vapor state. So states of matter can definitely tell you something about those intermolecular forces. While you might predict something had stronger intermolecular forces because it was hydrogen bonding, but the question said that the other substance had a higher boiling point, then you have to go with the stronger forces, and you just need to figure out what they are. And chances are it will come down to the fact that the London dispersion forces in that other substance are so large they overcome the hydrogen bonding in the other substance. And we'll work quite a few FRQs on that.